You are about to embark on a study of the branch of computer science theory known as automata theory or language theory. We're going to follow fairly closely a one-quarter course I gave at Stanford a few years ago. Its traditional number is CS154. This theory plays an important role in computer science. I am aware that many students don't see the importance of a mathematical approach to CS. The feeling is, just let me near a keyboard and let me code. It's quite common. In this introductory video, I'll try to give you some reasons why you should learn the material contained in the course. A number of years ago, Stanford took a survey of its graduates 5 years after they got their undergraduate degrees. What they wanted to find out was whether Stanford was teaching stuff that they actually used in their jobs. So computer science graduates naturally cited our introductory programming courses as the one they used most. No surprise here. Next came our sophomore level courses covering basic data structures and algorithms and systems software. Again, no surprise. But after the required courses, we found that CS154, the automata course on which this set of videos is based, was second after the database course. It was cited by 3 times as many as cited the introductory AI course, for example. So I want in the next few minutes to try to explain what it was about automata theory that impacted what our former students were doing in their professional lives. So let's see some of the ideas we're going to learn about in the course and how they appear in practice. One very commonly used idea is the regular expression, a simple notation for describing many of the patterns that arise naturally in practice. Many pieces of software that you might find yourself working on in the future need a simple input language to describe patterns. So you might well find yourself implementing some form of regular expressions. For example, many Unix text processing commands use a variety of regular expressions. This expression describes a line of text that has a letter A followed by any number of characters followed by the letter B. For a more modern example, the XML document markup language invites us to describe the structure of documents by a DTD, or document type definition. The DTD language consists of descriptions of elements such as the example given here. A person element consists of a name element, followed by an address element, followed by any number of child elements. Finite automata are another topic we'll see early on. They are, in fact, the way regular expression-based languages are implemented. They also have been used for decades to model electronic circuits, and in particular to help design good circuits. They have also been used to model protocols, and we'll give some examples later in this course. Especially, finite automata underlie the body of techniques known as model checking, which has been used to verify the correctness of both communication protocols and large electronic circuits. Another important aspect of the course is the context-free grammar. These are used to put a tree structure on strings, typically text strings, according to some recursive rules. They are an essential for describing the syntax of programming languages and are a part of every compiler. They also play an important role in describing the syntax of natural languages and are used in software that does machine translation and other natural language processing. And the DTDs we mentioned in connection with regular expressions are really context-free grammars. It is the single rules of a DTD that look like regular expressions. The topics we just mentioned are essentially tools for doing simple but important things, but there is a second broad theme in this course. There are fundamental limitations on our ability to compute. A computer scientist should be aware of these limitations, because only then can you avoid spending time attempting something that is impossible. One limitation is undecidability. There are problems that cannot be solved by computation. For example, you might imagine you could write a compiler that would refuse to compile programs that printed out dirty words. Even assuming you had a precise definition of what words were dirty, you can't do this. We're going to prove that there is no way to tell whether a program will ever print a particular word, or even whether it will ever print anything at all. And we also need to know about the class of problems called intractable. These are colloquially problems that we can solve, but whose solution takes time that is exponential in the input size. These problems generally need to be finessed in some way, such as by approximating the solution. The reality of the theory of intractability is quite a bit different from the colloquial version, but while the undecidable problems have been proved not to have any solution, for the intractable problems we have very strong evidence that they require exponential time but no proof. We'll explain all this when we get to the theory of NP completeness as the culmination of this course. So another thing you'll take away from this course is the ability to navigate the space of problems that you might encounter in a life of creative software construction. You will learn how to determine that a problem is undecidable and how to determine that it is intractable. That lets you avoid the problem altogether in the first case and to modify your approach in the second case. There are several less concrete benefits to this course. First, you will improve your skills at proving facts, especially inductive proofs, of which we'll do several in great detail. Now, I'm not one of the people who thinks that formal proofs of programs will ever be a serious software methodology. But as you construct code, you should have a sense of why what you're doing works the way it is supposed to. Often the trickiest parts of a program deal with trees, graphs, or other recursive structures. Understanding inductive proofs lets you at least formulate a reason why you think your method works, even if you don't try to dot the I's in a formal proof. We're also going to learn about a number of important abstractions: finite automata, regular expressions, context-free grammars, and varieties of pushdown automata and Turing machines. Some of the essential parts of this course are proving equivalences among the models. That is, any example of one model can be simulated by some instance of another model. The process of simulation across models is essentially the same as the modern approach to programming in layered abstractions, where you write programs at one layer using the primitives of the layer below. At Stanford, I found that a number of people taking the automata course were not computer scientists at all, but were mathematicians by inclination. That's cool. Welcome to those of you out there. I probably won't do things quite as formally as you would like, but more formally than the typical computer scientist likes. However, be warned that some in the past have found the subject sufficiently interesting that they saw the light and made major contributions to computer software. A case in point is Ken Thompson, the fellow who gave us Unix. Before doing Unix, Ken developed an interest in regular expressions and saw that they were an important part of a text editor. He worked out efficient ways to compile regular expressions into programs that could process text, and his algorithms are an important part of what we teach about the subject today. It should be no surprise that regular expressions form an integral part of so many Unix commands, and that these commands give more flexibility and power to Unix users than did those of earlier operating systems. Another interesting case is Jim Gray. Jim, before his mysterious disappearance, gave us many important ideas in the database field, including two-phase locking for concurrency control, for which he won the Turing Award. But I knew Jim when he was a student at Berkeley, and I was on leave there for a brief period. He did a thesis on two-way pushdown automata. We're not going to talk about them. They turn out to have been a backwater of the theory, and I'm sure Jim would agree. But they are related to ordinary pushdown automata, which we will talk about in connection with context-free grammars. What is interesting is that Gray told me quite a bit later that he decided to become a computer scientist because automata theory intrigued him. Only later did he switch into database systems, and I believe that the experience he got dealing formally with automata made him more capable as a designer of several very innovative systems. So here's a summary of what will be covered in the course. We'll start off with what are called regular languages. A language is just a set of strings, for example, the set of character strings that are valid Java programs. The regular languages are exactly those sets of strings that can be described by finite automata or regular expressions. This discussion will also introduce the important concept of non-determinism, machines that can magically turn into many machines that each do something independently but with a coordinated effect. This model of computation is fanciful, to say the least, but we'll see it plays a really important role in several places, including design of algorithms and in understanding the theory of intractable problems. We're then going to turn to properties of the regular languages. These properties include the ability to answer certain questions about finite automata and regular expressions that we cannot decide about programs in general. An example would be to tell whether a device makes an output in response to even one input. You can't tell for programs in general, but you can for finite automata. It is this tractability, our ability to understand what simple formalisms like finite automata or regular expressions do, that make them so very valuable when they can be used. We're also going to talk about closure properties of regular languages. For example, the union or intersection of two regular languages is also a regular language. The next big topic will be context-free languages. This is a somewhat larger class of languages than the regular languages, and they enable us to do things that you can't do with regular languages, such as match balanced parentheses or XML tags. We'll talk about two ways to describe such languages. First, by context-free grammars, a recursive system for generating strings, and then by pushdown automata, which are a generalization of the finite automata that we'll use for regular expressions. We'll then repeat our examination of decision properties and closure properties for this larger class of languages. Many of the things we can tell about regular languages that we cannot tell in general, we can also tell about context-free languages. But there are unfortunately some exceptions. Similarly, many of the operations under which regular languages are closed also yield a context-free language when applied to context-free languages. But again, we lose some operations. For example, context-free languages are closed under union, but not intersection. Next, we take up the largest class of languages that we can reasonably say can be dealt with by a computer, the recursively enumerable languages. We also look at the smaller but important subset of the recursively enumerable languages called the recursive languages. These are the languages for which there is an algorithm to tell whether or not a string is in the language. We introduce the Turing machine, an automaton in the spirit of the first kinds of automata we meet, finite and pushdown automata. The Turing machine is, however, much more powerful than either of these. In fact, it is as powerful as any model that has ever been thought of to answer the question, what can we compute? The payoff for the study of Turing machines is that we can answer the question of what can be decided by computation, or what can be computed by any means at all. We shall develop tools for showing that certain problems cannot be decided, that is, answered by a computer. The example we already mentioned, does a program print a dirty word, should give you an idea of what we can achieve. Finally, we're going to cover the theory of NP-completeness. The critical question is, what can we do with an algorithm that runs in time that is some polynomial in the length of the input? It would be lovely if we could distinguish between problems whose best algorithm took, say, n cubed time from those that could be solved in, say, n squared time. But no theory has ever been devised to be that precise for general problems, although the best running time for some problems is known. Fortunately, we can learn a lot by dividing problems into those that can be solved in some polynomial amount of time from those that apparently require exponential time. We'll give you the tools to do this, and Turing machines are the tool you need to build this theory, as well as the theory of what can be computed at all. This course follows the third edition of the textbook I wrote with John Hopcroft and Rajiv Motwani. You do not need to buy this book. The homeworks and exams will all be based on what you can learn by observing the slides and listening to my commentary on the slides. Okay, the following is optional and depends on what we decide to do about the page references in the homeworks. You will, incidentally, find as you do the homeworks that there are explanations when you make a mistake. These explanations refer to pages or sections in this book, but you do not need the book since the explanations, like the course material itself, are designed to be self-contained without your having to read the book. I ask one thing, however. Please do not download a free copy from a file sharing site or delete it if you have already done so. This book was published by Addison Wesley under a contract that dates back to 1967. At that time, there was no internet and it wasn't all that easy to produce books. Addison Wesley invested a good deal in the production of this book and its predecessors, and they deserve to recover their costs. It is stealing to download a copyrighted work without paying. There's no two ways to look at it. Admittedly, the world has changed, and recently I have started to put books on the web for free, download from my own Stanford web pages. You are welcome to what is freely given, but please do not take what is not offered gratis.